So I love calculus, and I think it's fun to look at derivations of different derivatives. And this one I'm particularly fond of. The first time I saw it, I thought it was interesting and cool, but I forgot how to derive it a few times, and I had to learn how to derive it a few times. It's not that hard to derive, but it's easy to get confused, but not anymore, and it's fun. So let's have a look at this. The derivative I'm talking about, and let me just choose a better color here. That's a yellow instead of red. How about orange? Okay, so the derivative I'm talking about is the derivative of y equals the inverse sine function. So the derivative of the inverse sine function, or the derivative of the inverse cos function. It's just the negative version of the derivative of the inverse sine function. So what is dy by dx of sine to the minus 1 of x, the inverse sine function? Okay, so that's what we're going to look at. All right, and I think it's pretty cool. But the first thing to note is we need to understand a general statement over here about derivatives of how derivatives of functions relate to their inverse functions. So dy by dx, the derivative of a given function, the derivative of y with respect to x, equals, and this is the statement we must know. This is the first piece of the puzzle. 1 over, so the reciprocal of the derivative of the inverse function. So that'll be dx by dy. So to say that again, the derivative of y with respect to x is equal to the reciprocal of the derivative of x with respect to y. So the derivative of a given function is equal to the reciprocal of the derivative of the inverse function of that initial function. Okay, so this is the first piece of the puzzle that we need to know. Okay, the second thing is we can make a statement. We can say that x equals sine of y. Okay, and that's just the definition of an inverse function. This is just noting what an inverse function is by definition. So you can like pick a value. So for instance, what is a sine of 30 degrees? So what is sine of pi over 6? That's 30 degrees, and the answer will be a half. Okay, and so you could say that the inverse sine of 1/2, for what value do you get a half? What value of sine? For what value of sine do you get a half? And the answer is pi over 6. So we could just swap this for x's and y's and we get this. Okay, so the definition of an inverse function is what value of the one gives the other. So we could just swap the x's and y and take away the inverse function. This is just by definition. Okay, great. So we need to keep this in the front of our brain as well as this. And in fact, we're going to use this as our template to solve the derivative, because here we have it in derivative form already. dy by dx equals 1 over dx by dy. So if I can find dx by dy and plug it in over here, I've got the answer. And I have an x over here. So I can take the derivative of x with respect to y. So let's do that. Okay, so dx by dy equals, well, the derivative of sine is just cos. So this is just cos of y. Okay, nice. So I could just plug this in over here. So dy by dx equals 1 over cos of y. Yay, I found the derivative of the inverse sine function. But it's in terms of y. And we don't want it to be in terms of y. We want it to be in terms of x. Okay, so what are we going to do? Well, we have y equals sine to the minus 1 of x. I could just plug that in. I could say dy by dx equals 1 over cos of sine to the minus 1x. Cos of the inverse sine function in terms of x. But that's a bit of a monstrous function. Okay, so we don't want to do that. We don't want to have a monstrous composite function with an inverse as an argument. That's going to be a bit messy. So what we're going to do, we're going to use Pythagoras. Pythagoras saves the day again. Okay, so we just remember, now we're dealing in terms of y here. We remember that, okay, sine squared y plus cos squared y equals 1. Okay, and we want to rearrange this because we want an expression for cos to plug in here. Okay, so we can say cos squared y equals 1 minus sine squared y. Okay, but there's no square over here, so we want to get rid of this. So we say cos of y, we take the square root, equals plus or minus the square root, that's a funky radical, of 1 minus sine squared of y. Okay, groovy. Now we have a plus or minus situation over here. Is it a plus or is it a minus? Okay, so we're going to think about this function. Okay, what does this function look like? Because we can't really take the inverse of sine. It's not invertible because it goes up and down and up and down. It's a wavy function. Okay, so we have to restrict the domain. And a common domain to restrict the sine function is, the sine function 2 is minus pi over 2 to pi over 2, then we get the straight line. So let's have a look at that. Okay, so if I have a sine function, it's going to be a wavy function. Okay, it's going to be it's going to be this wavy function. That's terrible. It's really bad. Can I do that? I better erase that. That's just atrocious. Bear with me. Bear with me. Okay, there we go. Okay, let's see if I can do better. Okay, let's try this again. It's probably going to be red now. Let's see. Is it still going to be yellow? Yes, it's still yellow. Great. Okay, so sine will look something like... Okay, that's good enough. Oh, okay, that's not really very good, but it's fine because we're going to restrict our attention to this bit over here. This is going to, oh, that's actually good. It gives me an opportunity to fix it up. I'm just going to go to here. So we're going to restrict our attention to minus pi over 2 to pi over 2. Okay, so it's this little bit over here that we're restricting our attention to. Okay, so between here and here, sine will take the values of between 1 and minus 1. Okay, so the inverse function, the domain of this function will be the image set of the inverse. Okay, so we're going to, and the image set of this will be the domain of the inverse. So these are really funky lines, artistic license. Okay, so this is going to be minus 1 and 1. And it's a reciprocal function, so it's reflected about x equals y. So it will look like, something like this. So, let's see, let me try that again. Try that again. This is the hardest part, me trying to draw these darn things. Okay, come on, you can do it. More artistic flair there. Okay, so it's going to be this way. It's going to be something like this. So over here it's going to be going this way, and over here it's going to be going this way. And what you will notice about this inverse function is if you take the derivative, if you look at the gradient of the curve at this point, it's going to be a vertical line. And the same thing at this point, it's going to be a vertical line. That's why we don't include minus 1 and 1 in the domain. So the domain of this function will be minus 1 to 1. Not including those endpoints. Okay, so now we've got to think about, this cos function. Okay, so this function, all of its values are going to be between, I told you a second ago that the image set is going to be this domain, so it's going to be pi over 2 to minus pi over 2. So all of the values of this function are going to be between pi over 2 and minus pi over 2, and we know that cos is positive. If you draw a cos little hill between I'm going to draw the cos one over here. Switch colors. I'll switch to, what's a cosy color? How about blue? Okay, so cos between minus pi over 2 and pi over 2 is just going to be a little hill. Like this, and you can see that that's all positive. So we know that this is going to be positive. Okay, great. Let me stay in blue just for fun. This blue looks nice. So now we can say that, maybe I should go to a new page. We can say that, what do we get? We got dy by dx of sine to the minus 1 equals 1 over the square root, positive square root of 1 minus, okay, I'm just going to go back and show you what I'm doing here. You see I have sine squared y. So I'm just putting this sine squared y in, okay? And I'll show you how I'm going to change that in a second. So sine squared y. But we want this in terms of x, so I haven't solved the problem. But look, we got a sine y over here. Okay, x equals sine y. That's how we started this whole business. Okay, so let me write that down. X equals sine y, right? Okay, so if I square both sides, x squared, oopsie, equals sine squared y. So I can stick an x squared into here. Okay, so this equals 1 over 1 minus x squared. Okay, so dy by dx, the derivative of the inverse sine function equals 1 over the square root of 1 minus x squared. That is our result. And that's pretty cool. I love that. And this is a cool, very cool derivative. And you've got to be careful. I was doing some integrals, and I sometimes get confused. If I get like, so we just have our result. Our result is dx by dy of the inverse sine function equals 1 over the square root of 1 minus x squared. Okay, and then maybe you're asked to find the antiderivative or the indefinite integral of 4 times 1 minus x squared to the half. Okay, and you see this and you're like, oh no, this is going to be hairy. But all you got to do is you got to rewrite this to like, oh, this is just a minus half, excuse me, minus half. You see this and you're like, oh, whoa, what's going on? This is going to be really hairy. But you just realize, okay, if I rewrite this, I can rewrite this as, well, this is just the square root. So you could rewrite this as this. And you're like, oh, so it's just 4 times 1 over the square root of 1 minus x squared. Okay, that's what this is asking you. And since, you know, the derivation and integration are opposites of each other, the answer is just going to be, oh, wait a minute, this is just the integral of this is just going to be sine. So the answer is, it's just going to be the integral of this is going to be 4 sine to the minus 1. It's not sine. Did I just say sine? I meant to say sine to the minus 1. This is just the integral of the inverse sine function is what I meant to say, plus c. Okay. And then you've solved this. You've solved this integral in a second just by realizing this. The scary looking business is just this. So yeah, this is one that I will start a problem like this doing integration by parts or thinking about substitution, and it gets hairy quickly, and all I got to do is remember this right over here. Okay, anyway, I thought this was a cool little derivation, and it's fun for me to go through it again. I hope you enjoyed. Thanks for watching.